computer. Excellent. Am I sharing my screen? That's the question. Okay, and we're on. Okay, excellent. I guess I can put my video to this show, right? Let's maybe see if I can get rid of that. That's good enough for me anyway. So, what's up, everybody? Welcome back. We're doing reverse engineering part 2 today. So, just if you were, I'm going to show hands who was here on Thursday. Okay, so about half, a little more than half. This is good. This reverse engineering stuff that we're going to be doing here is going to be more of the advanced technical tools and techniques which we can use, and some more advanced obfuscation methods. So if you guys weren't here on Thursday, just come to me afterwards, and we'll make sure we can solve this Thursday challenge before we move on to the Sunday ones. Are we recording? Yeah. Awesome. All right. This right up for announcements. We got nothing, so we'll move right on to the meeting plan. So you all know the drill, hopefully by this point, but just go to SIGPwny.com, put this in for the meeting flag, and you get 50 points. Hopefully by the end of this talk, you'll understand exactly what this meme is, and then we'll have more laughs about it than we just did. I thought it was pretty clever. A lot of this meeting is going to be talking about how can we solve reverse engineering challenges without actually reverse engineering. It's going to be fun. Okay, all right, I'm gonna move on. Of course, we can always revisit this in the future, and the slides will be posted, so if you didn't catch it here, we'll get to it. But some things that we're gonna talk about today, we're going to start with some tools and techniques which we can use. First one we're gonna talk about is symbolic execution. Next thing we're gonna move on to is an instruction counting side channel. Both of these are very popular for automating reverse engineering challenges in CTS. The symbolic execution has, but they both of course have more general purposes than just CTFs. And then we'll talk about some obfuscation which you may encounter when you're solving CTF REChals or just in the real world when people try to obfuscate the program so you can't understand how it works. Okay, so let's get started with symbolic execution. So like I said earlier, every concept which we talk each of those four have a corresponding challenge in reverse engineering part 2 on CTF. So go check that out. But let's get started with symbolic execution. So the premise of symbolic execution is given a constraint, the goal that it tries to solve is given some inputs which we provide. So maybe that's like some input on standard in, or maybe that's like a flag that we put as the command line parameter. And in a desired state that we want the program to be in at the end, let's solve for the inputs which allow us to reach the outputs. And so the way that this works, so you probably see why this is already really handy, because if you're here on Thursday, you kind of see a common theme, right? Where the CTF reverse engineering challenges say, please give me the flag, and it's going to tell you if it's correct or not. And so in this case, the desired output state is when it prints that's correct, or when it doesn't, in fact, doesn't print incorrect. And then we can solve for the standard input, and we'll just print the flag for you. So a very high-level way that this works is an interpreter will step through the instructions of the program, and it will build a symbolic expression of the output state with regard to the symbolic input state. And so when I say symbolic, it's really just a fancy name for we just make things variables that we can solve for almost algebraically at the end. So let's look at an example. They have a program which looks like this. We say like x equals something. Maybe this is the input that we provide. So we provide x. The next thing that it does is it computes a new variable, or it computes a new value of y, which is equal to x squared. And then it computes z equals y plus 1. And so our objective is to find some x such that z equals 5. And so what we can do is we can do the reverse engineering step ourselves, where we can say, okay, well, we know z equals y plus 1, and where we can kind of reason that, you know, x can be, if x is 2, then, you know, we can write the algebraic expression and compute that. But what symbolic execution does is it steps through the program and generates the algebraic expression for z in terms of x for us. And then there's also the constraint solvers, which takes that symbolic expression and figures out, given our constraints, which in this case is z equals 5 and x is greater than 0, and it can do that, compute that the x input that it should provide is 2. Because without that second constraint, there are multiple solutions, right? I chose this example because if x equals positive 2, we get 5, and if x equals negative 2, we also get 5. And so there may be multiple solutions, and so you have to add as many constraints as necessary to get a unique value for your input. So some actually ways that this is done in CTF-child, which you'll see soon, is I want to solve for some input such that it prints correct, right? And that input I'm going to constrain such that every character is a printable character, right? Because what if there's a null byte that works and it prints correct or something? That's not the flag. Right? So we're going to constrain our flag, like x is greater than 0. We're going to say the ASCII value is greater than hex 20, which is like a space or something, and less than the capital Z, so it's printable. We'll get to that. So what are some usages of symbolic execution? So as we were just talking about, really we focused on, we can reverse engineer, we can solve RE-childs without actually reversing it. But some other interesting usages is for automated pwn, for example. This is beyond just CTS now and just in general. Given a val, like an output state which we want to occur, which is where we control the instruction pointer, we can solve for some input such that that occurs. So say there's a vulnerable function, and I could say, Angr, please solve for me an input such that the buffer is overflow, and it will determine that, following these steps, it will generate an expression and solve for it such that we can override the instruction pointer and control the control flow. And then also something I worked on this summer, which I thought was fun, is automated ROP gadget discovery. So we're going to talk about this more when it comes to like Thursday, probably next Sunday, what a ROP gadget is. But just know that really symbolic execution can be used to understand the semantics of what assembly is trying to say. So it can be a useful tool in that regard. So the tool that we're going to use for symbolic execution is called Angr. And Angr is a symbolic execution tool for binaries. So in this case, we're going to be looking at using it on Linux binaries, specifically x86 Linux binaries. And here's a very awesome, like code golfed way that you can use Angr to solve an RE-child. So for every line 1, 2, 3, 4, I put the description of what that corresponding line does. And so after we import Angr, we can say create a new project and give it the brute, which is the name of the challenge. And give me a simulation manager. And so the simulation manager is what actually emulates the program, steps through it, and generates that expression, right, of the inputs and the outputs. And so what I want to say is, simulation manager, please explore all the possible paths of the program such that correct is in S posix dumps. And so what this is saying, the one, if you're familiar, is actually the file descriptor for standard out. So really what this is a fancy way of saying is such that it prints correct to the terminal, right? And then what I can do is say, I'm going to choose the first path that you found such that correct is printed. And I'm going to ask you, what is the standard in, because there's a file descriptor for standard in, which gave me that output state of correct. And this will just print the flag. Yeah, I mean, it really is magic. And so there's a challenge called Angr, which is on CTF, which has this kind of premise. The difference is that it's the flag you provide to the command line argument and not standard in. So when you have a flag, it's like, please give me the flag and you type it in on standard in. This is a script, type of script you can just apply it to. For standard in or command line parameters, I have here a link to an Angr script, which I always use. And I've annotated every line with a descriptive comment on exactly what it does. So I'm going to post these slides and I encourage you to click it, especially when you're looking at Angr. You can directly apply the script to it, but I encourage you to read over every line to try to understand what's actually going on with Angr. Because as high level as that is, you can use Angr to instrument binaries at a low level. So you can set register contents and you can directly solve for registers, you can solve for memory. And a lot of times it's not so easy. In higher level CTFs, they don't often just ask you for the flag on the command line. They may give you a puzzle and you actually want to solve for some memory, given that the another memory value, which indicates that the puzzle solved correctly is set. So, okay. All right, moving on. So that was symbolic execution. Any questions on symbolic execution? Excellent. Again, I'll post these slides and you can click this link here in a sec. So next up is instruction counting. So instruction counting is a cool side channel in certain CTF reverse engineering challenges. So the real premise here is that, again, we're trying to solve this challenge without doing any of the nasty reversing. So this binary can be as evil and as disgusting and irreversible as it possibly can. But if it satisfies some of these criteria, we can probably do it automatically using an instruction counting side channel. What does that mean? The premise of instruction counting side channels is that the more instructions that are executed tells you that you're getting closer to the correct answer. So let's put an example. Maybe I should erase that because that's motivation. So consider that this challenge terminates early at the first character mismatch, right? In fact, let's make it even easier and say that it terminates immediately if the flag lengths are not the same, right? So if my true flag is flag, if I type flag in the command line, it's going to say that's correct, right? That's what exactly what our objective is. So if I type A, press enter, I count the number of instructions which are run, and it yields 100 instructions executed for typing A. That's because our logic is, if the lengths differ, stop, right? And so if I type another A, it's also going to be 100 instructions. This is, or close to 100 instructions, right? Because technically there's another, probably that stir compare is probably not constant time either, so close to 100 instructions, right? Because the lengths differ, so it stops, right? Because then the checking code happens after. And then as soon as I try to type 3 A's, same thing, probably around 100 instructions. But as soon as I type 4 A's, we observe that the flag lengths are true, or they're the same. And so now it's going to continue to like flag checking logic, which will now execute 250 instructions. Right, so here we can have this like guess, okay, it's probably 4 characters long. And we haven't even looked at any of the assembly yet, right? This is just using our inference, some heuristics. Okay, so now that we know that the flag length, we conclude that the flag length is 4 characters. What we can do is say, if our implementation says, we're asking for the first character A, if it's not true, terminate. Right, then for every incorrect character, A, B, C, D, it will always execute the same amount of instructions, right? So if I change this to A's, 250 instructions. If I change this to B, A's, 250 instructions, because it's never going to check the next character. As soon as I turn this to F, it's going to execute 275 instructions because now I check the next character because the first character is correct. Does that kind of make sense? And then so now we infer that the first character is F, we repeat that process, we use the next character is L, because we're still going to guess 4 characters. They're just we know the first 2, and then eventually we can conclude that we can actually leave the entire flag out. So that's the premise of instruction counting. Any questions on that? Cool. Does anybody know how to write a challenge which is resistant to instruction counting? The question is, can anybody tell me a method to write a challenge that compares 2 strings which is resistant to instruction counting side channels? Yes, I like that. And you said just don't break it. Excellent ideas. Yes, Thomas. Good. Excellent. Yes. Any other ideas? Base 64. That's an interesting one. We have to look into how base 64 works. Okay, I like that idea. Let's break each of those down individually. So the first thing we heard was don't terminate early, and that's exactly correct. So what that's referring to is like a constant time comparison, such that if I have flags, if I have another 4 character string, I expect it to always step through every character regardless. And so we can have some flag, right? We can say it's correct or not. And as soon as we encounter the wrong thing, we can set that flag to be incorrect, but we still continue to finish the string. So it's not efficient, right? And it shouldn't be, because that's the whole point of a constant time comparison. So that's resistant to instruction counting. And when you do like timing attacks on stuff, it's really the same premise. And so constant time is a really good approach. And then I heard next is do some like pseudo random or just some like random amount of instructions. And I love that idea because it's really like a trolley idea. So I really like that. To say like, do some instructions while a number is less than some randomly generated number. So that's excellent. And then we also heard Thomas, you said hash it and compare the hashes. And that's also good because a flag being similar does not imply that their hashes would be similar. And so you can know useful information about counting instructions on the hash comparison. And then base 64, we have to be a little careful with that. I'm not sure if base 64 preserves the order. So we might have to be careful with that. I'll have to look into base 64 to see if that works. Awesome. Yeah, right. So you may still be able to deduce the length and get other things. So this also depends on something else that's important, is that it depends on the order that the flag is traversed. Because if I'm guessing the first character and I'm permuting it and I'm looking at how the instruction counting changes after permuting the first character, if that's really checking this third character, and I guess that, then I deduce what it is, I move on to the second character, and that's going to be, it's changing. Maybe it checks characters in reverse. Then my deduction is wrong here. So we still have to guess, right, what we're doing. And it might check in this order here, corresponding to these things. So I should first flip F and then I should flip A if I actually want to see it sequentially, because then I observe that all characters that I change L to don't indicate any change in instruction count. So it's completely dependent on like a naive implementation of a string comparison, or an efficient operation. You can guess, you can infer, oh, maybe they're being tricky about it, and let's try to guess it in reverse order. You can do all sorts of heuristics here, and people have, and that's what I want to say next, is the tools that exist for this already is a very popular one called, well, first, there's a binary instrumentation framework called Intel's PIN, their PIN tool. One of its many abilities is to count how many instructions were executed during the duration of your program. And then this GitHub project exists only to use that tool to automate reverse engineering challenges. Someone posted slides that you can click on and explore it. It's going to do exactly that. If you check forward, you can check the length, and if you reverse, and I'm not sure what else you can do. That's really all you need. I think it was actually Dan who showed me this one. During our last CPF, there's a way that you can use Valgrind, and it will count. It says that it's instructions, but I'm not exactly sure if they're instructions. They're just like unique branches or something like that. But regardless, you can use Valgrind to count, have a useful metric, which is maybe correlated with the number of instructions executed, to do some logical deductions. So here I gave an example. If my flag was SIGPwny, if it's all A's, I get 148,862 instructions. And if it's actually the correct string, it's going to compare more characters, and then you get 100 more instructions executed. Any questions on that? Any questions on Zoom this one? Excellent. Okay, so that really wraps up our automated tooling, reverse engineering process. I'm going to talk briefly about obfuscation techniques and a little bit about how we can tackle them. But really, it's going to come down to time and pain to tackle all of these. The first one we're going to talk about is self-modifying code. And the premise here is exactly how it sounds. Code in this case referring to the assembly, the instructions that are executed. They can actually write to the instructions which are currently being executed or will be executed in a couple instructions, and it will change the behavior of the program. And so let's see. I wrote here some specifics of how this is done. You can use some functions called nmap and nprotect, which change the permissions of the memory pages. By default, code is read-only. You cannot say, okay, now my next the instruction after me is now going to be an XOR instruction. You can't do that usually, because for obvious security reasons, right? If a program can write code to executable regions, then you can just jump there. Right? It's like shell code. So it's not ideal. So in any case, when you encounter a reverse engineering question or problem like a CTF challenge, which busts out protect your nmap, you need to start sweating because it's something crazy going to happen with them writing dynamic instructions, change instructions, and it really makes static analysis almost useless. So the static analysis, you can observe that that's what's going on, but it's very hard from a static analysis perspective in Ghidra to be like, okay, here's the functionality of the program because it changes. And so the way we combat this usually is going to be debugging it. unfortunately. So you actually have to bust out GDB, step through it, and GDB will handle these nicely. And then you can look for patterns. You can look to see how it's obfuscated, and then maybe you can write some tooling. The Python script which reads the binary and tries to understand it. But debugging is the best way to go about understanding self-modifying code. Yeah, so I wrote a note here. See the signals challenge. So the signals challenge is self-modifying. It's approachable though, and we can totally talk about it after when you guys are looking at it. Next up, we're going to talk about virtual machine obfuscation. So this one really is the worst. Honestly, I think that it's the most torture. So the premise of virtual machine obfuscation is that instead of giving you a binary which does something, it is the program, they're going to give you a binary which is a virtual machine or like an emulator, which emulates another program which actually does the thing. So let's look at like virtual machines that already exist. So is everyone familiar with like the Java virtual machine? It's an executable which, given Java bytecode, will execute the Java bytecode, right? And so in the case of VM obfuscation, we're going to have an emulator or a virtual machine, but it's going to execute its own custom architecture, which no one's ever seen before, to complete its objective or run its program. And the reason why it does this is that there are so many good tools about reverse engineering, like x86 and other popular instruction sets. Like there's decompilers, right? But if I invent my own custom architecture that no one's ever seen, I call it x87 or something. I mean, that probably already exists, to be honest. But maybe it does some like crazy, it has some crazy instructions for like how it does branching or something like that. There's no way that I'm going to get this into a decompilable state. I'm going to have to spend a lot of time looking at first, how does the emulator execute its bytecode? Next, how do I disassemble or decompile that bytecode? So really, VM is just like a time state. It really takes forever. Commercial like VM obfuscation, an example is VM Protect. What they do is they charge you money, and they will obfuscate your binaries with their proprietary like virtual machine. So it's like a custom architecture. And it's like they mapped your binary into that, and it's very effective. I think only recently they came out with tools that could unpack the virtual machine and sort of reverse it back into some x86 stuff. This summer, UAU CTF, we had a VM challenge. It's called Obfuscated. So I wrote that, and there's an architecture called ELVM, which is like a reduced instruction set. And I mapped that to ROP gadgets, which we'll learn about next Sunday probably. And then for CTFD, there's a challenge. I called it hell because that's all I can describe it as. It's also VM obfuscation. So after you've solved literally every other challenge, then only then I probably recommend that you start to look at this challenge. What you need to do, yeah.
Real quick, obfuscating was solved by 2 people. One person going to that. Don't attempt that unless you have literally nothing else to do. It's an unbelievably cool example.
Yeah, thank you. It's cool, but VM, just anything VM obfuscation, it's just a time sink, man. It just takes so long to understand it and to reverse it. You have to write your own tools and disassemblers, decompilers, lots of crying involved, it appears. But yeah, I'd be happy to talk about that in more detail. Okay, so yeah, that was all for today's meeting. Just to recap, talk about Angr for symbolic execution. Everybody check out the slides, look at that script, apply it to the challenge called Angr, which exists on CTF. And then we talked about instruction counting. So I have a link to a couple tools that's going to be useful for the side channel challenge. Signals is an example of an application which uses self-modifying code. And so look at that in Angr first, understand what's going on, and then debug it. And finally, what else did we talk about? Last thing we just talked about. VM obfuscation. Yeah. Go check out the last challenge on CTF if you have time. But what I want everybody to do is first solve everything from RE1. Then you can move on to RE2. And I'll be walking around helping everybody. We'll do, if anyone has the same question, we can all huddle around the same laptop and we'll go over it together. That's it. That's all I got. So just practice. Feel free to ask literally any question as soon as you get the tiniest bit stuck. I'd be happy to help. Next meeting is going to be next Thursday. We're going to do intro to Pwn. So that's like after we reverse engineer a program, what input can we put on the program such that we can take control of the application? Hopefully, there's going to be some more advanced techniques with that. It may occur next Sunday, or we may have to push that back. We'll let you know.
We are.
Okay. All right, that's all I got. Take a look at those, Chelsea. Work with your neighbor if you want. I'll be around.